Roman concrete contains a specific chemical architecture that uses salt water to trigger a reaction. It grows stratlingite crystals within its matrix, physically sealing its own cracks as they form. Our modern infrastructure relies on Portland cement. This material is designed to be chemically inert, with its sand and gravel components intended to remain unchanged by their environment. When seawater inevitably breaches that Portland cement, the salt water triggers an alkali-silica reaction. It attacks the internal steel rebar, causing the metal to rust and expand, which fractures the structure from the inside out. Modern engineering attempts to completely repel the elements. This creates a rigid, brittle structure that eventually succumbs to the constant pressure of the ocean. In the Mediterranean, Roman breakwaters have faced those exact same saltwater conditions for 2 millennia. Many of these harbor installations are still standing. Analysis of core samples taken from these piers reveals that seawater facilitates the ongoing growth of the concrete's mineral matrix. Roman builders used a combination of volcanic ash and lime, specifically formulated to remain chemically active, utilizing the ocean as a component of its curing process. The Romans engineered a material that converts environmental stress into a mechanism for its own survival. To achieve this, the Romans combined lime with reactive volcanic ash sourced near the Bay of Naples. For their mortar, they utilized a technique called hot mixing. By adding highly reactive quicklime directly to the dry mix, they triggered an intense exothermic reaction as soon as water was introduced. This intense high-heat process leaves behind millimeter-scale white chunks known as lime clasts, which are scattered throughout the finished concrete. Researchers previously assumed these clasts were the result of poor mixing. However, recent studies from MIT show they function as engineered reservoirs of reactive calcium. Through hot mixing, the Romans trapped potential chemical energy within the concrete matrix, where it stays dormant until triggered by the environment. When these structures are submerged, the alkaline seawater percolates into the concrete and dissolves the volcanic glass within the ash, initiating a pozzolanic reaction. This data shows rare, highly stable minerals like aluminous, tobermorite, and philipsite. These crystallized at low temperatures inside the ancient stone long after it hardened. These structures grow in flat, interlocking platy shapes. This microscopic architecture physically reinforces the cementing matrix. Unlike the expanding gels in modern cement, these interlocking crystals increase the concrete's resistance to fracture and allow it to absorb seismic shock over centuries. Even with this reinforcement, the physical force of the ocean will eventually cause microcracks to form. When seawater enters these gaps, it triggers a second reaction. The water reaches the porous lime clasts. The calcium inside dissolves, creating a saturated solution that fills the surrounding void. This solution recrystallizes as calcium carbonate, creating a physical bridge across the gap, sealing the crack before it can spread. Because of this autonomous healing cycle, Roman marine concrete can maintain and even increase its compressive strength the longer it remains in the ocean. Modern Portland cement production requires extreme heat and generates significant CO2 emissions. The Roman method uses natural volcanic ash and functions at much lower temperatures. As global sea levels rise and storm surges intensify, coastal infrastructure is facing environmental loads that exceed current design standards. We can shift away from building inert barriers designed to block out nature and instead engineer materials that use the environment to maintain themselves. Explore the materials and systems that build our world. Click the subscribe button, activate the bell, and see you in the next scientific investigation into the boundaries of modern engineering, only on TEMBODocs.